Hello, my name is Eric Enouen, and today I'll be presenting my work that I did this summer, PICSR, Prototype-Informed Cross-Silo Router for Federated Learning. I worked on this project as part of the Auton Lab, and I worked with Dr. Sebastian Caldas under the direction of Professor Artur Dubrovsky. To start, I just want to give a brief motivation for this work. So the goal is that we want to be able to find a method that can combine the prediction capabilities of multiple different hospitals, but each hospital can have their own patient distribution based off location, among other factors. And so we want to be able to build a router that can map an individual sample to the hospital best fit to perform well on it, so that they can use their model in an explainable manner. And so, as you can see in this figure, Model A may have some distribution in blue of their own patients, and Model B may have this other distribution in red. And so if we have an input in this input space, we want the router to be able to map these inputs to the models that would be best prepared to answer whether or not they have some positive class or not. And so the approach that we use is that we try to embed prototypes in the prediction. So we initialize a prototype for each silo as the mean patient that is inside of that silo in their training data set. And our goal is to first encode our sample X and then compare its similarity to each of these using an inverted L2 distance, and then utilize these similarities for our final predictions for a weighting for each silo. And then we utilize this router output as the weights for an ensemble of experts. So we also pass this patient X to each expert to get its output, and then ensemble their predictions according to the router output to get the final prediction. So the experiments that we run are on the heart disease dataset from UCI, and we split up this dataset according to how Flamby does it. So it splits according to the natural splits. So each hospital that contributed to the dataset is siloed away. So Cleveland, Hungary, Switzerland, and VA Long Beach. And we assume that we cannot share data between these hospitals. And then the goal is to predict whether or not a patient has heart disease. So for our results, we show that we're not only able to outperform the local models, but also able to outperform a naive ensemble. So you can see that in this graph on the top, our method is able to outperform both the ensemble, which is just a constant weighting for each expert, and the local models. So each silo gets to use their own model for their own test or data set. In addition, this routing also aligns up well with intuition. So in each of these figures on the bottom, you can see that the model who's being tested on, their test data set is mostly routed to their own model that they trained. But you can also see that for both Cleveland and Hungarian, they utilize each other because there is some shared information that they can benefit from. But however, for Switzerland, mostly every sample that in the Switzerland test data set is sent back to the Switzerland model. And then the VA model, you can see that it still sends a majority of the samples to itself, but it utilizes a wider range of different models. So in conclusion, we're not only able to improve the predictive performance, but these prototypes also help ground the routing in the underlying data distribution. So as we can see on the left, TRESS BPS is the resting blood pressure when they're admitted. And we can see that for the Switzerland data set, this blue is those samples that are routed to the Switzerland model, and the prototype is in the training set. how many samples, or the average sample for this feature. And so you can see that these line up much closer than all of the samples that are not sent to the Switzerland model. And so we hope to continue trying to explore this prototype idea and how they can be used to explain the differences between institutions. Thank you.